Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about nuclear reactor shielding. Basically, this is part 3 of my radiation shielding. So let's dive deep into the source. So reactors. Now, thankfully, Earth has a shield known as atmosphere that is 100 km thick. So we got it. We are protected. And we also have a magnetosphere on top of that to protect the atmosphere itself. So we good. We are safe from cosmic background radiation. And unless sun precisely starts to sneeze on us, we good. So where is our source? Like where the heck we are creating radiation? Well, reactors. That's the biggest source of radiation for humanity. Basically, if you ever talk to someone, it's like, okay, you are exposed to radiation. Where do you work? 99% of the time, it would be reactors. Now, there's another issue with reactors is that not only they give you alpha, they also give you beta, they also give you gamma. And on top of that, like if these three is not enough to poof you out of existence, they're like, how about some neutrons? So this puppy gives you everything. And here's the this is one critical aspect that you must understand. Even with fusion and fission, there is no off in this sort of system. Yes, you can stop the reaction, but there is no exactly stopping the reaction, specifically in fission power plants. For example, let's say I have seen this stupidity in way too many small modular reactor where they have like, this is the reactor, something bad happened, earthquake or something happened, I'm just going to press the controller, it's going to shut down everything. That reduces the reaction, does not eliminates it. You cannot have like, oh, there is not even a single neutron that is acting. That's not how it works. It's probabilities. Like if you have 100% throttle, maximum as it can go, 0 does not mean absolute 0. It's like, okay, majority of it is done. Now, here's the problem part. When you have something like this, a nuclear fission reactor, it has daughter products, meaning once you had the fission, stuff is there, be it xenon, be it something else. And all those stuffs, they are hot. How hot? Generally, it said you are talking about around 10% to 20% of the reactor's thermal capacity. Like 100% if it's here, 10 to 20% would be there if you turn everything off. You are like go all in with control rods. If the reactor has been on for let's say a few days, that's what will happen. So if any working reactor that is like online for a few days, yeah, there is no off. So what does off mean? Well, off means pray to God. You turn off, you insert all the control rods and keep pumping the cooling water. As long as cooling water is there, as long as you're removing the 10 to 20% heat away from it, it's good, it's safe. But if that part fails, and ironically, that's what failed in Chernobyl, basically, that's what they were trying to test. Like, what if something goes wrong and we lose power? How do we keep running the coolant pumps? Basically, as long as the diesel generator takes such time. So you need to switch over, so to say. So, and Fukushima also had the same issue where it's like, okay, earthquake happened, control rods, boom, we safe. No, sir. You just entered the hell. Now, the hell phase is make sure it has cooling water continuously running to it. And to give you more context, remember spent fuel requires 2 years in cooling ponds. 2 years. So if any Tom, Dick and Harry says, oh, we're just going to turn it off. Yeah, no. And then we come to the fusion part of it. Like there is no daughter product. Yes, it makes tritium. And on top of that, the shell that is inside, meaning let's say something worst happened. Let's say some war happened and somebody fired a pew into it and it goes boom. This puppy will make everything around it radioactive because the inside, the first wall would be so radioactive. And you can see that in the design. Every company that is working on it properly, every lab that is working on it, they're designing robotics from day one to replace anything that is inside because that would be idiotically radioactive. Not little bit. Idiotically. Now, of course, it will pile up. So day one, it will be like minor radiation. Day 500, yeah, no. So there is no quote-unquote off in reactors. Once it becomes radioactive, yeah. And this sort of system, their best hope from ITER is that once this is decommissioned, let's say you had a plan, it worked for, let's say 50 years, then you have to decommission it. Sooner or later, you have to decommission it. You decommission it. Everything's supposed to go to background radiation level in 100 years. Not joking. So that's why any Tom, Dick, and Harry reactor can be just turned off. No. Just no. Then we come to the fission part of it. Now, what is fission? Fission is a very good thing of divorce. Basically, you have a family and you just boim it. You diversify it, and then you have like basically neutron inserting itself, making it unstable, and then you have two daughter products. Now while you have that daughter product, that itself is not that interesting, but it does have neutron. Now these neutron allow you to create this cycle again and again, what we call chain reaction. Now if it happens exponentially, we call it runaway reaction or boom, and generally reactors cannot go boom simply because the fuel itself is contaminated, as in like it's not enriched to boom levels, so it cannot do that. Now, what about these neutrons? What is specific about them? Well, they're fast neutron. What does that mean? That they're traveling a bit fast. How fast? 14,000 kilometers per second. What does that mean? That simply means they're too goddamn fast, meaning if you do not have very high enriched uranium next to it, yeah, it's not going to do anything. It's just going to go through your reactor. So you may be like, okay, that's a problem. So what do? Well, we chill them down. We are like, we take them from 14,000 kilometers per second to be like, hey, how about less than 3 kilometers per second? How about that? We chill down. So how do we chill it down? Well, we apply the universal solvent, water. Water chills it down. You're like, you Bruce Lee that puppy. You're just like, chill, bro. So that allows our reactors to work. And water is the primary reason we can even make a fusion reactor without too much hassle. So, and water basically absorbs the energy. Basically, this energy gets into water. Now, water is not a crystal structure. It's not ice. It's a liquid form. So, it does not have a structure. So, neutron does not cause damage to it. It does irradiate it over time, but does not cause damage to it. So, water is water. And you can run it through your coolant pump. And you can run it through your steam cycle. If it's especially pressurized or directly boiling reactor, you can do that. So, you can do a lot of things with water. And water is protecting everything around it. That's the first line of defense. Water. Water is taking care of everything. Heavy water is just deuterium. So, that's how you protect everything. Water is the first line of defense. Now, water does sacrifice itself. First, it heats up. Second, sacrifices slowly over time. Plutonium, as in like just one proton in the hydrogen, over time gets married to a basically neutron. That causes some issue, but it's like, we good. But then a threesome happens. Another neutron gets inside, and then it becomes tritium, aka radioactive, aka the very thing that Fukushima plant is dumping into the ocean now. Is that an issue? Not in the quantities. It's like, it's there, yes. Can it be traced? Yes. But is that an issue? Nope. So that's the whole point. That's why we have reactors. That's the first line, water. After that, what do you do after that? Well, here's a simple answer. Super thick. It does not matter what you use. If you're using steel, just use a lot of it. If you're using concrete, use a lot of it. That's it. You do not apply logic to it. You just like go YOLO it. If your mathematics says 1 foot of concrete should be enough for, you put 3 foot of concrete. You do not discuss it. You do not cut cost on it, especially at the reactor core. Around the building, you can cut cost as much as you want. But at the reactor core itself, you go overkill. And there's another aspect of it. Once coolant pump shuts down and heat is not being taken away, the reactor is completely off. Let that be very clear. Reactor is off. You have inserted all the control rod. The material will melt. And it has so much internal heat that almost nothing can withstand it. Like this happens to the reactor grade concrete, like highest grade concrete we have. It just punches through it. The elephant foot in Chernobyl, that's the thing that happens to it. So you have to be very mindful. That's why I say like there is no off in a reactor. You just hopefully off it in, like practically 26,000 years when the last remainder will be completely, background radiation. So this is very critical. That's why you put as much of it as possible. So that's how we take care of fission part of it. Just put as much of it as you can and put as much water around it as you can. Then we come to fusion part of it. Now, fission is basically a good thing of divorce. This is the worst thing. This is a marriage. So what we do is basically force marriage between deuterium and tritium. Basically two things. We're forcing them into marriage and making them into one helium. Now that puppy dumps a lot of energy. It's too painful. So it dumps too much energy. Now we get fast neutron. This time neutron is even more powerful, even more faster. And that allows us to hopefully continue the chain reaction. Everything is good. A problem is that it happens in vacuum. When I talk about nuclear reaction, like exact reaction spot is surrounded by water. Here, the reaction spot is in vacuum. If you're not making a boom boom device, it's in a vacuum, because how you are going to do that reaction? It requires super hot temperature. How do you heat something to super hot? You isolate it, basically put it in a vacuum. You plasmafy it, and then you heat that puppy up. So it works. So far, so good. But it's in vacuum, meaning the neutrons that are coming out has nothing to tamper it. There is no Bruce Lee there. So what does that mean? That simply means this first wall is getting bombarded by super duper hyper fast neutrons. It's just getting bammed into it. Now, neutron is very weird. Sometimes it will just go through you. You'll be like, me good, you did nothing to me. Sometimes it will knock your crystal lattice away, so this thing will literally turn into fuzz after few years or even few months, and sometimes you could literally get inserted itself, making it into radioactive, and all these three things will happen in different ratios. So the first wall is the weakest link in this power plant design. Whatever you see this sort of thing, this is first wall. And that's why whenever you see anybody seriously working on the plants, they are like, hey, we have to develop the robotics to replace things inside. Yeah, that's the reason. This everything you see inside is radioactive. How hot it will get? Well, we do not have real data because again, nobody has been running this plant for even a year, so to say. So we do not know how hot it will get, radioactively speaking. But our mathematics suggests hot, as in like, whoa, hot. So that's our first layer. It has to hold back the atmosphere pressure, which is not that big of a deal from a proper metal point of view. Like, we got this, we good. But in terms of neutron bombardment, it's like, bro, what the hell you're doing? So it gets brutally annihilated. So what do we do to protect the whole structure? Well, we put cooling or shielding, whatever you want to call it. Generally, they are both in the same. After that, so once you have first wall, basically you put your first wall, you generally put your coolant system, whatever the coolant may be it liquid, be it some salt. Generally it's going to be water in the first generation reactors. So that water hopefully absorbs majority of the neutron after that. So your water heats up, everything is safe after that cooling jacket, after that shielding layer. Other people have thought of putting liquid lithium inside the reactor to protect this first wall itself, because be mindful, that's the most vulnerable place, the most expensive part. So you may want to extend its lifespan. So people have prescribed to the idea of putting liquid lithium that is just flowing through it, absorbing it, acting as a breeder reactor, so neutron damage would be reduced, and you will also have requirement parts out of it. So that's how we do it. You have cooling, shielding after you basically have the first wall. Now, first wall can't be helped. It has to suffer. It has to suffer. We can't do much about it. However, this cooling layer is the reason why you can have magnets there. Now, would it be wise from an engineering point of view to put the magnet directly just behind the first wall? Absolutely, you can do that. That's how almost all startups are doing it. Now, I'm like, wait a minute. If startups are doing it and they're showing positive results, why the heck these people are not doing it? Well, that's like a very short-term, basically shorts selling your stock, so to say. So they're going to show you a reactor that works. That's a practical, actual reactor. It works. It will give energy, and they will sell you stocks. You will buy it. And then they're like, hey, what happened to that reactor? Yeah, we turned it off. It's like, why? Yeah, the super hyper expensive magnets that we had to use, many of them requiring liquid helium, yeah, they did not last long. In this design, it will last hopefully for 50 years. In design where it's directly behind the first wall, yeah, good luck getting 2 years out of it. Now, of course, 2 years is more than enough to show people, more than enough to wow the crowd. And then you're like, take your money and piss on you, and I'm out. Like Hyperloop did, or Theranos did, or Solar Roadway did. You get the point. So that's why that's the easiest way to figure out who is taking fusion seriously and who is just trolling for money. So if you see a design where you have first wall and no proper thought put into shielding just after that, and just magnetic coil is just there, yeah, no, it's not gonna last very long. Heck, there is one design that many scientists are like, dude, it's not a good idea. This tokamak, it has enough thick in the core that core heat can, core neutron flux can be absorbed without having too much hassle. Other design, the core is too thin, very thin. It's like almost like an apple stick in the center. And they are designing it, and they're like, yeah, that's pushing it. Right now, they are dealing with that. It's like, yeah, it's pushing, but it's an experimental reactor. They're not designing it to run as a power plant, more as a research thing. So I get it, but you get the point. Like, that's how serious it is. Like, it's one thing to show you, oh, I made it, it worked for 1 minute and 1 month and all that. But it's another to design something that works for 50 years, hopefully. So fusion is really, really hard to do. On top of that, it has worse flux than fission. Basically, if you are making a reactor that is 1 gigawatt of thermal energy output, how much neutron flux is coming out of fission systems versus fusion? Fusion would be much worse. So this first wall would be annihilated, and the coolant hope that it can handle it. And some people have suggested to put like basically a solder kind of paste, a mix of 2 salts, so it can absorb enough neutron flux. It's brutal, basically. TLDR, it's brutal. So that's why it's not so easy, where people are like, oh, this will be cheap. No, you're going to go bankrupt in just first wall. And I'm not even going to talk about coolant blanket or hyper expensive magnets. Now, whenever we are talking about radiation shielding, you have to understand, we are generally talking about elemental levels. We are not talking compounds, alloys. Of course, they do play a role, but generally, whenever you are talking about radiation, you're talking about what exactly happens to the atom. Water does get radioactive, but it generally, whenever we are talking about it, we are talking about hydrogen in it. Would oxygen be radioactive if it's exposed to too much of it? Yes, over time, but generally it's very low. And generally hydrogen, from a probability point of view, generally takes it. So the mathematical way of understanding that is neutron cross-section area. And if you ever wondered what the heck actual nuclear physicists study, that's what they study. Neutron cross-section are the key vectors. So we generally have multiple categories of elements. So one of the element category is moderator. So if you watch Chernobyl, carbon and hydrogen, these are the best moderators we have, meaning throttle. If you are like, hey, so feather the throttles, carbon, like a Chernobyl reactor where you had the fuel surrounded by carbon, graphite. Why? That puppy took super duper hyper fast, basically neutron flux, and chilled it down. It's like, bro, relax, chill, man. And water was there to make sure the graphite is safe, and not to mention like heat to extract the heat also. So everything was fine. Graphite was like a throttle body. Everything was working just fine. Hydrogen was taking care of it, carbon was taking remainder of edge off, everything was just fine. These are the best tools for moderation. But what if you want to stop it? That means you have to do something with neutron. So we go into absorber category, meaning you just eat it up. So you go into boron. Boron and sand. Boron is the first solution you have. You have iridium, and then you have the naughty puppy of xenon. And this is the most brutal part of a fission reactor. Some designs, not all designs are vulnerable to it, but many designs are vulnerable to it, is that you create it, and if you mismanage it, xenon would be created at a much exponential rate compared to neutron flux. Neutron flux will not poof it out of existence, and then you could reach a point where you just like increase the throttle and neutron flux starts to come up, but your temperature does not go up of a reactor. You're like, why? Xenon pit. Xenon is just eating it away. Too much xenon, xenon is eating it away. And the moment xenon burns off, now, of course, hopefully the reactor is designed properly. This will not lead that. Hopefully, before that happens, control software should be like, hey, we just went through xenon pit. Relax. Apply some chill pill. So, and then we have cadmium. Of course, these are just few elements. Be mindful. That's what nuclear physicists study. If you want to do that, go into PhD. And then we have, how do you shield something? Let's say you have to transport a neutron source, californium, you want to ship that puppy. You have to find something like this. This is basically hydrocarbon box, plastic, so to say, but it has boron ingested into it. Like there's a lot of boron there. That's a really good way of stopping neutron. Now, what about the building? Like, let's say neutron, you took care of the reactor. Let's say the fusion reactor, you took care of the reactor. What after that? Well, you're never going to put that directly outside in the air. So we use boronated concrete. Now, this puppy, boronated concrete, is the backbone of nuclear industry. Basically, how do you make sure that this puppy survives? Boronated concrete. The main structure just after the reactor core is made out of this puppy. And a lot of boron is poured into it. And it's super duper hyper thick, unless it's made in Soviet Union. So this is the second line of defense, and this puppy works. So we are safe, we're good. This is on an elemental level. Now, I also wanted to cover space just for the heck of it. Well, space is very brutal for all living things, and it has multiple categories of hell. For example, it has, what if sun sneezes accidentally, coronal mass ejection, that will dump very high energy charge particles. Then you have supernova, even higher charge particles. So a lot of stuff where you are just getting bombarded by a lot of things. So how do you do that? Well, here's the deal. This is one aspect that people genuinely do not go about Apollo missions, is that whenever you're talking about radiation, no matter how brutal it is, it's not going to be poof you. It's not a 50 caliber pew. It's not like that. So you can see that in Chernobyl, like people were alive, like they saw into the reactor, they were alive for a very long time. And space is bad, but not as bad as a reactor core. So if you can survive looking into a reactor core a few days, you're going to be fine in space. And in Apollo mission, how did they navigate the van element? Orbit. They were going super duper fast, faster than orbital velocity, and the angles were adjusted in such a way that it reduced their exposure to the minimum viable level. And not to mention, this was in 70s. Somehow people don't understand that back then we did not care about safety. It was not invented yet. And this was Cold War. Money was no object. People were ready to sacrifice themselves. Trust me. So in those sort of ecosystem, that's there. And why ISS has not went out of existence? Well, it's below the Van Allen radiation belt. It's basically being protected by it. So if you want to go outside of this Van Allen radiation belt, basically moon, Mars, or whatever have you, in those sort of scenario, we need something that is safeguarding us for long duration. Now, if we go to the moon, go to the Mars, then we can take care of situation because we can bury ourselves. But what the hell are you going to do during the transit or in deep space? For that reason, we need some serious shielding, and we need shielding for everything: cosmic ray particles, charged particles, alpha, beta, gamma, everything. We need shielding on top of shielding. You need some serious shielding basically. So water is still the best. Ideally, that's what we're gonna do, but you can understand that, like let's say you have Orion spacecraft. How the heck you're gonna put a water curtain around it? And if you put a water curtain all around it, while it would be awesome, but it won't be thick enough because you cannot have that much payload mass. So for that reason, like we want to use water, but we are limited by it. So we generally use some mix of it. Of course, there will be water curtains in some places, strategic places that will be there. And then we use a carried mix. For example, my personal favorite is Z shielding. This is built by Z grading. Basically, you take carbon fiber, you lay a layer of heavy metal, basically aluminum, iron, steel, whatever have you. You take a layer of it, you deposit it, vacuum, you deposit it. Then you do another layer. Then you do another layer of different materials. How do you select the material? It has to go in reducing densities, meaning it has to keep going up in periodic table. So you have one lighter, even lighter, even lighter. You keep doing this, and this layer material has much better radiation shielding properties compared to almost everything else. So even if you have much thicker material that is awesome, it will be like this will bitch slap it. So we use it. Now, earlier version of it was a layered composite, meaning you had structure, you keep layering different elements. That does work. That's how ISS is built. However, that's a very sloppy app, and that creates an issue where it's like you have a structure, then you put that fundamentally reduces your payload. So idea with Z shielding is that this will be your structure. Basically, this is your stuff. You built it on it, and once you have built it, it's like, okay, good. Like you do not, it's like basically how we upgraded from chassis, basically frame and chassis model to carbon fiber monocoque, same design here. So your CubeSat will be literally built out of this, so you do not need extra space for shielding, and everything will be shielded. And that's the primary reason why a lot of R&D is going into that. Big satellite, geostationary, they have mass budget to have shielding, but CubeSat, while it is a big industry, they do not last long. Why they do not last long? Electronics do not last long inside them. You can send a Raspberry Pi up there, you can send Arduino up there, which people have sent. It will work, but it will not last very long. So to make sure that your investment in space lasts longer, you have to use shielding like this. So this is one option. Then you have future long-term scientific option of boron nitride nanotubes, this puppy basically. Now idea with NASA's long-term goal is that we're going to build a material that would be a structural material. Like this is a structural material, same is we are hoping that we're going to build something like this, meaning the fabric itself that we're going to design would be the structural material. It won't be like, oh, we build the structure, then we are covering it. No, it will be the material itself used for the construction would be the shielding itself. Then we're going to have really next-gen shielding. And can we do that? In chemistry? Yes. In physics? Yes. Economically, we are still struggling a bit. And not to mention mass production of this puppy is still a bit difficult. We are getting there, but it's difficult. So this is how we're going to take care of space radiation. So this was my presentation on basically radiation part of things. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.